this lesson 7 is velocity and other rates of change. So basically we start looking at position, velocity, and acceleration. And officially what we're doing is this falls into the idea of applications of derivatives. Okay, derivatives have a whole bunch of applications, and physics is one of the big applications of derivatives. So we'll go through information and see what we can get here. So notice it says, if you have taken a physics class, this will seem familiar. So, and I don't know exactly where you guys are at in physics, but you've started talking about the velocity and acceleration, right? You've talked about, that type of stuff. So, we have been using 2 different notations for derivatives, okay? And so there's 2 people credited with coming up with calculus. And that's where this comes from here. But in Lagrange notation, the prime mark, so when we do y prime or f prime of x, the prime mark is part of Lagrange's notation. And that's one we use the most. That's one we like the better, isn't it? Because it's just easier to do, easier to read, so, but that was from Lagrange. The original notation goes back to Leibniz. I can't remember how to say his name. Okay, but Leibniz, whatever. But his notation, notice it says here, it's a helpful reminder for the units of the notation. So since the derivative is a division process, the units will always be the y-axis divided by the x-axis. And so y units divided by the x-axis. And so that's why we often see the dy dx. Okay, and I will often read that as the derivative of y with respect to x. Now, a little bit about the derivative. Okay, suppose that s equals f of t gives the distance in feet of an object from a fixed position as a function of time t in seconds. What is the common term for ds dt? Okay. You guys see that that's velocity? Because this is the derivative. S is the position function, right? S and x are the 2 different ways you often see the position function. Do you guys use S in, what do you guys use in physics? No, but I mean like for the position function. Delta x. Okay, so not going to be the same there, I guess. But so the idea that this is the change in distance over change in time. Okay, so when we talk about ds dt, it's the derivative of position, and the derivative of position is velocity. Now, with that in mind, describe the following notation in real world terms. So when they're saying ds dt, and this, I read this as the derivative of s with respect to t evaluated when t is 4. Okay? What is that? What is that that we're looking at here? And we talked in a way about being velocity, right? But remember, when it is the derivative evaluated at a point, it's that instantaneous rate of change. If you remember, we talked about that back in Unit 1, right? Maybe a little. I think we talked about it at the beginning of Unit 2. I feel like maybe in 2.1. But it's that IROC, instantaneous rate of change. And in this case, it's the instantaneous rate of change. And if you think about this as being distance divided by time, it's going to be feet per second of the object at when? When t equals 4, so 4 seconds. Okay? I'm trying to think how I have this written here. Now, if I just write IROC, is that enough, or should I write instantaneous rate of change? I mean, and here's the deal. I don't want you guys to look back and be like, what's IROC? So, I'm going to use instantaneous rate of change, but then I'm also going to say it's the instantaneous rate of change in feet per second when t equals 4 seconds. Did I get everything there? I think I did. I should say instantaneous rate of change of an object, whatever, you know. Instantaneous rate of change, yeah. Should say of the object there. Thoughts on C? What does f prime of 4 equals 18 mean? Okay. And the only tweak that I would do is I would throw in the word velocity there, right? Okay. So yeah, I have when t equals 4 seconds, the velocity of the object is 18 feet per second. So when t equals 4 seconds, the velocity of the object is 18 feet per second. And note, this is a positive velocity, yes? We're going to talk a lot in this lesson about positives, negatives, what do they mean in the sense of velocity, acceleration, all of that. And because this is a positive velocity, this tells me the object is moving away from a fixed point. So generally speaking, so we think, you know, positive, we think in a forward motion, right? So because this is positive velocity, moving away from a fixed point. So if you want to throw that in, you can. Positive velocity, object is moving away from a fixed point. Okay, the bottom of the page. Did Neil Armstrong step off the lunar module and pick up a moon rock from the surface of the moon on July 20th, 1969? I thought it was an accepted fact, but there must be some. I take it there's discussion out there about whether it's actually.
I think it's staged.
Okay, so I'll be honest. Until I'd read this, I hadn't really heard that. So,
Flag,
huh?
flag waves.
No, I didn't know that. So.
There's no wind.
Interesting. Okay. So no, until because it kind of, you know, caught me off guard there. So I obviously haven't paid attention to the right thing there. But okay, if he did, and this is interesting to think about, if he did, scientists say the rock would have had a velocity of 24 meters per second. Okay, here in America, we don't think meters per second. So, well, then it translates to 86 kilometers per hour, which doesn't help either. I thought there was a miles per hour here, but there's not. So, but still, 86 kilometers per hour. I don't know. Have you guys ever, on my vehicle, I have that button I accidentally hit sometimes and change my vehicle from miles per hour to kilometers per hour, and all of a sudden I'm going a lot faster down the road.
My mom's.
It doesn't seem like a really this.
So, no, I usually look down, I'm like, whoa, wait, how am I going that fast? And then it's like, oh, wait, okay. We're not really going that fast. Okay, so the height of the moon rock can be modeled by the function s of t. Find the velocity and acceleration of the moon rock as a function of time. So, okay, how are we going to find the velocity? We talked about this yesterday. Nope, just first derivative is velocity. Okay, you can flip back to yesterday's notes. So, I better change off of this orange. I don't know how well this orange is showing up for you guys, but so the first derivative of position is velocity. And it is commonplace to make, by me stating S prime of t equals v of t, I am telling my grader, whoever's grading my AP test, right, that I understand that the first derivative of position is velocity. So that's often a connection you want to make. What's the derivative? Okay, 24 minus 1.6t. That is velocity. What about acceleration? What is acceleration then? It's the second derivative of position, or it's the first derivative of velocity, or it's acceleration. Okay? And what is that there?
Negative 1.6.
Yeah. Negative 1.6. And officially, what would be the label of the acceleration?
Meters per second.
Yeah. Meters per second, or meters per second squared, right? Okay. Yeah, so note, the acceleration will be the acceleration of gravity on the moon. But officially, don't we say there's no gravity on the moon? Okay. Okay, B. How long will it take for the rock to reach a maximum height? Okay, think here. Huh? Is the physics drawing the same as the algebra drawing?
No.
Yeah.
It's pretty
Okay.
similar, yes.
I mean, for algebra, for math, it's a parabola is what we usually draw here. So, which, notice, what is this? It's an upside down parabola, isn't it? Negative x squared. It's a parabola, so when we're trying to find the max, we're trying to find the top of our parabola. Where are we going to find the top of that parabola?
Whenever the velocity is 0.
When velocity is 0. Okay? Because velocity is 0, it's going up. It has that pause, right? Before it starts going back down. Not that it really pauses, but yet it's that brief moment in time. So we're going to set our velocity equal to 0. So I'm going to say 24 minus 1.6t equals 0. And we're going to do the math. Oh well, I'll write as negative 1.6t equals negative 24. Do the division, and t is 15 according to my notes. 15 what? Seconds? Okay. So, how long does it take for the rock to reach the maximum height? 15 seconds. How high did the rock go, and when did it hit the ground? So how do I figure out how high the rock went? Yeah, it reached a max height at 15 seconds. So how high did the rock go? Well, how high was it at 15 seconds? So you're doing S of 15, which is 24 times 15 minus 0.8 times 15 squared. It's a plug it into the calculator type thing in my brain. Sorry, I did forget to check something this morning that I meant to check. Okay, agree with the 180. Now, when did it hit the ground?
30 seconds.
Okay. So why 30 seconds?
Because it's twice the time it took to get to the top.
Interesting. I had to pause it like, oh, he already did the math here. Because we're actually going to do it mathematically, because we need to be able to do it mathematically as well. Okay? So what's the math behind it? But I see what he's saying. A parabola is symmetric, right? So that is a parabola. A parabola is symmetric. If halfway through it's at its max, then double that. I understand. Now, mathematically, what's the equation we set up?
We literally just had this do times 2.
Okay.
Yeah.
Okay. I'm just thinking there's going to be times that the math behind here is, we need to know the math behind it. So maybe not. I don't know, but
It would be when the velocity is opposite of what it was when it left the ground.
okay. But we don't know that.
Okay.
I guess you could you find that? I don't know. I was not thinking in terms of velocity.
Okay.
I'm thinking more along the algebra 2 type level here of thinking. Of what's the height of the ground?
0.
0. So we want to know when what is 0?
1.
Okay. The y value is 0, or in other words, we want to know when the position is 0. Because notice the height of the moon rock can be modeled by this function. So you want to know when the position is 0. In other words, the y value is 0, but its position is 0. So here you're trying to find s of, or not plugging in 0, not what I meant, when s of t, there we go, equals 0. So 24t minus 8/10 t squared equals 0. If I factor out a GCF of t and also a GCF of negative 0.8 works quite well actually, because 24 divided by 8/10 is 30. So you end up with a t minus 30 in parentheses. No, because I factored out a negative 8/10 t. That way I can make this t positive. So if I factor out, if it's negative 8/10 t squared and I factor out negative 8/10 t, we're left with t. If it's 24t, I divide by negative 8/10 t, it's negative 30. Because the idea, the algebra behind it is you set what? Both parts equal to 0, right? And so when you set both parts equal to 0, I'm going to end up with t equals 0 and t equals 30. Which answer do I need here? The 30. What's the 0? When it started, right? It was at the ground when it started, and then it was at the ground at the end. So the answer we need for this particular piece is 30 seconds. Okay.
That's what we had stuff.
So, now, was I disagreeing with the 30 there? No. But, how's the algebra behind it work? Okay. And I mean, on AP, could you, if you make this statement here and then say that, is that enough? Maybe. You know, it just depends what you have to do, right? But something like making this statement right here is, you know, could be considered important in that case. Okay, moving along. I'm not sure there's any way I can get through these notes in 2 days. I'm too slow. Okay. Last lesson, we defined S of t as the position function of a particle or object. However, y equals f of x can be used to represent many different quantities, such as amount of rainfall, temperature of yams, volume of a cone, people infected by a virus, random situations there.
Yeah.
The derivative will help us discuss how these quantities change at any given moment in time, right? Because remember, derivative is slope of the tangent line, and slope is rate of change. So when we talk about derivative, it's rate of change here. So suppose W of x is the daily quantity of water in gallons required by a palm tree of height x feet. So my palm tree that is x feet tall requires W of x gallons of water each day. Okay? Explain the meaning of each expression in a complete sentence including units. So what does W of 25 equals 38 mean?
Trees 25 feet tall.
Okay. My 25 feet palm tree requires 38 gallons of water per day. Don't ask me the truth behind this because I have no idea. Okay? I'm going provided problem, right? Just like it came out of the textbook. Remember, I didn't write these, okay? So 25 feet tall palm tree requires 38 gallons of water per day. Okay. So that right there is just looking at W of 25 equals 38, just understanding what the information means. This is huge in my brain. W negative 1 of 38 equals 25. What does that negative 1 represent? That's the inverse. Okay, so remember, this is not a derivative. This is not, this is inverse. If you remember inverse switches our input and output values. I don't know, do you guys know how to say this one?
The same thing.
It's the same thing in a way.
Is it 38 gallons of water a day need to go inside a 25-foot palm tree?
Doesn't need to go inside that palm tree.
How about the 38 gallons of water determines how tall the tree is, so to speak.
That's what he said.
That's exactly what I said.
Not what you say.
It was.
I want to see how you're going to put this water into the palm tree. That's what I'm trying to visualize.
He's gonna give it a little IV.
I'm like, I'm envisioning, and this is the weird thing, is like opening the lid and pouring the water in. And I'm like,
No, it's like
How do we
the
open
water
the tree?
wants
I don't
to
know,
do
but
it.
that's what my brain went to. Just go with it, okay?
Like the water needs to find the tree, otherwise it won't be like it's not water. It needs to find the tree.
Okay, so my wording here in my notes, when a palm tree requires 38 gallons of water per day, the palm tree is 25 feet tall. So my input here to the equation is the 38. The output is the 25, and so that's what we're, that's the distinction here. So when a palm tree requires 38 gallons of water per day, the palm tree is 25 feet tall. So we see palm trees. Are there underground, like, watering systems or something? Because how? I really question this
They have a
equation.
large root system. Yeah.
I mean, they could. Okay, see. The whole point of this lesson here, whole point of this unit. W prime of 25 equals 6.
The velocity of the trees.
The leaves are waving.
So fast as a tree.
Velocity? Really? Velocity? Okay.
Like grows 6 feet something.
It's not about the tree growing.
It uses 6 gallons something.
So how about think 6 gallons more? It's because remember, so derivative is rate of change, yes? And what is W? W is the gallons, how is it stated? The gallons of water required per day, right? So this is the rate of change of the gallons of water per day. The input is still the 25, the height of the palm tree. So a 25-foot palm tree, the derivative is indicating that it is increased, because it's a positive derivative here, it is increasing 6 gallons. How do I want to say that? I don't have the wording right. The amount of water needed daily is increasing at a rate of 6 gallons per foot. Okay? Not the velocity is increasing 6 feet per whatever. Or gallons. Yeah, no. Okay, so when the palm tree is 25 feet tall. The amount of water needed daily is increasing at a rate of 6 gallons per foot. Okay, so when a palm tree is 25 feet tall, the amount of water needed daily is increasing at a rate of 6 gallons per foot. And we understand why it was increasing. It was increasing because that 6 was a positive 6, right? Okay. Let's go to the bottom and try this again. Well, not exactly. You'll notice there in the middle it says it is an acceptable practice to merely just say rate of change for some moment in time or other event to represent the instantaneous rate of change. In other words, you won't always hear instantaneous. Then there will be other instances where you must decipher the task from the scenario. Let's look at example 4. Suppose C of T represents the cost in dollars per day to air condition your Florida beach house when the temperature outside is T degrees Fahrenheit. Explain the meaning of C prime of 90 equals 0.37 in a complete sentence. So let's see. C of T is the cost in dollars per day to air condition your Florida beach house. The temperature outside is T degrees Fahrenheit. Okay, you got it? What can we start off with? What's the easy part? Huh? I'm looking at the input to begin with. When the
Temperature is 90.
when the temperature is 90 degrees, right?
Yeah.
Is that what you're saying?
Yeah.
Yeah. I mean, like, to me, that's the easy part. I know the input is 90. I know 90 represents degrees Fahrenheit. So when the temperature is 90 degrees Fahrenheit outside, this is derivative, right? And derivative of C. So C is the cost in dollars per day to air condition, okay? So if this is C prime, then it's changing. Yes, it's the rate of change. So the cost in dollars per day to air condition is changing at a rate of 37 cents per day. Does that make sense? So, when the temperature is 90 degrees, and I am going to specify outside just because that was the problem, right? When the temperature is 90 degrees outside, the AC cost is, again, it's increasing because it's positive, right? Is increasing at a rate of 37 cents per day. Approximate the cost of air conditioning your beach house when the temperature is 94 degrees, given that C of 90 is 2.64 and C prime of 90 is 0.37. We know the derivative equals 37, yes? In order to find rate of change, think in terms of rate of change of like finding slope, yes? And so, approximate the cost, think of it this way. We know the ordered pair, 90, 2.64, right? We want to know 90, what, or excuse me, not 90, what, 94, right? We know at 90 degrees, it's 2.64. At 94, we want to know that. And we know the derivative, right? So we can set this up as, I think of like, it's average rate of change. C of 94 minus C of 90 over 94 minus 90. And that's going to equal the 0.37. Plug in everything you know and do the math. We can do this because we know the rate of change is 37 cents. So I'm trying to find C of 94 minus 2.64 over 4 equals 0.37. Let's see, I already did some math there. If I multiply the 4 over, C of 94 minus 2.64 is going to be equal to 1.48. And so then if you add the 2.64 over 1.48 plus 2.64 is 412, and that would be per day. Okay. I know I kind of went through that last one quickly because I saw time was getting close. Although I have a little bit more time left than I thought I did. Always the case.
So the diff is 0.37 times 3 plus the 260, like 2.64, like that.
That is essentially what we did. Mathematically, that's what we did. This is just the setup we used. Okay. Okay. Move my tab. We will pick up there On Monday, I might just have to plan 2 more days because
Where my toes?
Ooh.
When my dog was
I have to be realistic there. It's not happening.